Hi, here we are. It's Lesson 2, Polynomial Arithmetic. And I know in Lesson 1 at the end I promised you we'd be solving equations. I lied. But in order to solve equations, you first have to be able to work with variables. Since you've already taken Algebra 1, we should assume that you have seen polynomials. That's the x's and y's and letters and numbers all mixed up. I want to try to clarify, first of all, what a polynomial is. And most of the polynomials we will work with will be one variable polynomials. That is, only the letter x. We'll see a couple of examples that have other letters in them. A polynomial, and this is very important, and perhaps you won't find this in your textbook. A polynomial is a number where the place values are variables, are powers of a variable. For example, let's look at the first graphic. We see 3x squared plus 2x plus 7, and right next to it you see 327. X is the place value. That is, we have the x place, the x squared's place, just as in whole numbers we have the tens place and the 10 squared or hundreds place. Obviously the ones place is the constant. The difference between 327 and 3x squared plus 2x plus 7 is twofold. One is that in the 327, the place values, the hundreds, tens, and ones, are understood by the location of the digits. The 3, for example, is in the hundreds place. In the polynomial, the place value is shown. The x is there, the x squared is there. Otherwise, it's the same. In fact, if x equals 10, then 3x squared plus 2x plus 7 is exactly 327. But x doesn't have to be 10. It could be any number you'd like. And in fact, later on, we will check some of our arithmetic problems with polynomials by plugging in x equals 10, because it really is very simple to evaluate a polynomial when x is 10, because you have the tens place and the hundreds place, just like you did back in second or third grade. I want to step away from polynomials for a second and talk about numbers, because I know most of the students I've run across in my teaching career have a very poor idea about place value. And the key to polynomials is recognizing that the x and the x squared, the x cubed are place values. So let's look at the next visual, and it has two numbers. I call the first number 300 negative 27. And I ask my students, what is 300 negative 27 equal? And they have no idea. Well, again, place value. The 3 is in the hundreds place, the negative 2 is in the tens place, and the 7 is in the ones place. That is 300 minus 20 plus 7, which I believe is 287. The reason I bring this up is because with polynomials, since the place value is given, we can have negative numbers as well as positive numbers as the coefficients, that is, the numbers in front of the x or x squared, which are equivalent to the digits in our place values in our whole numbers. The second number on your screen, 357. You may giggle a little bit. Halfty, what does that mean? Well, if something is in a tens place, we put a ty next to it, right? 50, 60, 70, this is halfty. What's that equal to? 300s. Half a 10 is 5, 7 ones makes 312. Again, with polynomials, we could use fractions as our coefficients. You could have a half x or a half x squared or 2/3 x to the third, etc. Let's take a look at the next visual. This is some other examples of things that you can do with a polynomial because the place values, the powers of x, are shown. The first one has 3x squared minus 4x plus 2/3. Again, we have a negative number in there and a fractional number. You couldn't do that with whole numbers. The second one, 5x cubed plus the square root of 7x, has an irrational, a square root number, in one of the place values in front of the x. Also notice in the second polynomial, there's no square term and there's no whole number or constant term. That is, if this, for example, if we had a number like 5070, we'd have a 0 in the hundreds place and a 0 in the ones place. We don't need those zeros in polynomials because the place value is shown. So we just put a 5 in front of the x cubed and a plus square root of 7 in front of the x. Now, what we're going to do in the rest of this lesson is add, subtract, and multiply polynomials. And the thing I want to impress upon you is that assuming you can add, subtract, and multiply whole numbers, then polynomials are no different. But we're going to go ahead and restate the rules. For example, in adding whole numbers, the key is lining up the place values. Adding all the numbers in the ones place together, the numbers in the tens place together, the numbers in the hundreds place together. You can't add a number in the tens place to a number in the hundreds place. You just can't do that. It's against the law. It's against the law because adding is really a form of counting, and you can only count or add things that are alike. Now, the nice thing about polynomials is there's no carrying. Some of you may think back to first or second or third grade, and you struggled with learning how to add when you had to come down a column and then carry something over to the tens place, add down the tens place, and carry something over to the hundreds place. We don't worry about that because you can have a number as a coefficient in front of the x or x squared that's bigger than 9 because there's no limit, there's no place as such. So let's take a look at the first addition problem, which is 2x cubed plus 3x squared plus 7x minus 4 plus 5x squared minus 9x minus 2. Now, the first step we said is to line up the place values. And notice beneath the original problem is the problem rewritten with the squareds and the x and the numbers all lined up. All we have to do now is simply add. Since there's no x cubed number in the bottom polynomial, we just bring down the 2x cubed. Just as if there was a 2,000 in our top number and no digit in the thousands place if we were adding two whole numbers. 3 plus 5 is 8, so we have plus 8x squared. A positive 7 and negative 9 is negative 2, so we have negative 2x. And a negative 4 and a negative 2 is negative 6. Thus, our answer. Now, let's take a look at the next visual because it looks the same problem. It is the same problem. It shows the original problem and the answer. But also what we're going to do, and this is a very good way to check polynomial arithmetic problems, is plug in, that is substitute, x equals 10. So if we do that, the 2x cubed plus 3x squared plus 7x minus 4 becomes 2,000 plus 300 plus 70, 7 tens, minus 4, or 2,366. And the 5x squared becomes 500 minus 90 minus 2, which is 408. When you add those two numbers up, you get 2,774. If we plug x equals 10 into the answer, the 2x cubed is 2,000 plus 8x squared plus 800 minus 2x minus 20 minus 6. 2,000 plus 800 minus 20 minus 6 is 2,774. Our answer checks. If it checks for 10, you know you are right. And it's very, very important in any work you do in algebra, wherever possible, to check your work. Okay. Now, that takes care of adding. How about multiplying? I always like to ask people, first of all, what multiplying is. And you should remember back from third grade that multiplying is repeated addition. So when we multiply, we're actually learning a way to add quickly. So 3 times 8 means 8 plus 8 plus 8. Now, some people learn to multiply and just do it by rote, having no understanding of what they're doing. So what I'd like you to do is take a look at this next visual, a multiplication problem right out of your 4th or 5th grade arithmetic book. 427 times 381. Notice there's an arrow from the 3 to the 2, or between the 3 and the 2. 3 times 2 is 6. My question to you is, where does the 6 go? Now, most people I ask this of, they want to start multiplying with 1 times 7 and then 1 times 2 and then put it, no. 3 times 2 is 6. Where does the 6 go? The 6 goes in the thousands place. And the reason it does is because the 3 is in the hundreds place and the 2 is in the tens place. And when we multiply digit times digit, 3 times 2, and place value times place value. In this case, hundreds times tens. So the 6,000 is the answer, and therefore the 6 goes in the thousands place. If you can understand this, and again, Multiplication is digit times digit and place value times place value. Then multiplying polynomials is a breeze. And the reason is very simple. Each polynomial is made up of these terms called monomials, mono being one nomial. So for example, if I was to multiply 2x squared by a negative 3x, that's a monomial, 2x squared, by another monomial, negative 3x. How would I do that? Well, the coefficients, the number, the constant in front of the variable, the x or the x squared, is just like a digit. And we said multiplication is digit times digit. So I would multiply 2 times negative 3. And since we multiply place value times place value, I'd multiply the x squared times the x. So as you can see in the next visual, 2x squared multiplied by negative 3x equals negative 6x cubed, since x squared times x is x cubed. Notice also each of the monomials are in parentheses, and there's no symbol between the parentheses. You may recall from your previous experience in algebra that if you have 2 letters or a number in a letter without any symbol in between, that means multiplication. We don't want to use an x to show multiplication because then we get that confused with the x for the variable x. And therefore we use parentheses to separate the terms and to show that it's multiplication. If those parentheses weren't there, you might think it was 2x squared minus 3x, a subtraction problem. Okay, now let's take a look at a multiplication problem in polynomials that's not very different from a multiplication problem you might have done in, let's say, 4th grade. The next visual shows you 3x minus 5 times 3x squared minus 4x plus 3. To me, this is no different than multiplying a 2-digit number by a 3-digit number. We do it exactly the same as we did it in 4th or 5th grade, and I'm sure as we still would do it today if you didn't have a calculator handy. The only difference is that we multiply x times x, it's x squared, rather than 10 times 10 goes in hundreds place. So the first thing we do, we start with the bottom number, the rightmost column or place value, the negative 5, and the next visual shows us that we multiply the negative 5 first by positive 3, then by negative 4x, and then by 3x squared. And we get negative 15x squared plus 20x minus 15, simply multiplying each of those terms by negative 5. Okay? The next visual takes us to the second line, because now we're multiplying by the 3x term. And obviously when I multiply 3x times positive 3, I get 9x. And notice the 9x is lined up with the 20x, because we're eventually going to add, just like we did with whole numbers, and we only can add things that are the same. We add x's and x's, x squareds and x squareds. Continuing on, multiplying by 3x, we get negative 12x squared, and we get 9x cubed. Now, just as you did in 4th grade, we add down the columns. And we already saw we know how to add polynomials, so we just write the answer, 9x cubed minus 27x squared plus 29x minus 15. What should we do next? If you've been paying attention, you know that we should check. Any possible problem in algebra, dealing with variables, equations, you need to be able to check. And if you recall, I recommended that we check using x equals 10. So let's go ahead and go to the next visual, and you'll see side by side the original problem with the answer, 3x minus 5 times 3x squared minus 4x plus 3, and the answer. And to the right of it, what each of those polynomials would be if x was 10. That is 263 times 25 is 6575. 6,575. To check now, all we got to do is take the 9x cubed minus 27x squared plus 29x minus 15, the answer, and plug in 10. 9x cubed becomes 9,000, minus 27x squared becomes minus 2,700. The plus 29x is plus 29 times 10 plus 290 minus 15. If you add those numbers up, and feel free to use a calculator, you'll get 6,575. We know our answer is correct. And as you can see, except for the idea of multiplying x times x squared and getting x cubed, this problem is no different than multiplying a 2-digit number by a 3-digit number back in elementary school. Now, I'm sure in Algebra 1 class, and you may have already done this in Algebra 2 class, you've been introduced to the FOIL method. For a number of years, I taught this without recognizing what FOIL meant, that the F stands for first and the O is outer, etc. Who cares? You want to call it the FOIL method? Call it the FOIL method. You want to call it, Fred's method or Mary's method or whatever your name is? That's fine too. Let's take a look at the next visual, which shows you what the FOIL method does. It simply takes a binomial, like bicycle meaning two monomials in a term, and then another binomial, and multiplying them, the parentheses indicating multiplication. And we start at the left of the first binomial and simply multiply that 2x by each of the terms in the second binomial. 2x times 3x is 6x squared. 2x times negative 4 is negative 8x. Then we multiply positive 3 by each of those two terms. 3 times 3x is plus 9x, and 3 times negative 4 is negative 12. Notice the answer, 6x squared minus 8x plus 9x minus 12, is not the final answer because we need to combine like terms. You wouldn't leave a number like 320 and 35. You say 355. So we combine the negative 8x and the plus 9x, and our final answer is 6x squared plus x minus 12. Checking. Notice there's a check on there. We plug in x equals 10. 2x plus 3 is 23. 3x minus 4 is 26. 23 times 26 is 598. 6x squared becomes 600 plus 10 minus 12 is also 598. It checks. Some of my students have liked to do all multiplication horizontally using this FOIL method. That is, if you want, go back and try to do the previous problem that had the binomial and the trinomial with 3 terms in it using this horizontal or FOIL method. Or you could go back and try using that original method, I call the vertical method, like we did back in 3rd or 4th grade, to solve 2x plus 3 times 3x minus 4, lining numbers up and putting it down and adding along the columns. Either way, you should get the same answer. There is not one right way to do mathematics. Anybody who says that, I'm sorry, I just can't trust. If your teacher says that, don't tell him I said that. But the point is that, to me, there's various ways to get to the right answer. So whichever of these two methods feels more comfortable, makes more sense, is, quote, easier for you as a student, use that method. And if you were in my class, I'd say, I don't care how you do it, as long as the way you do it makes sense and you typically get the right answer. Okay. When we learned how to multiply back in 3rd grade, or maybe you were really bright and did it in 2nd grade, we looked at patterns. We saw that, for example, as you multiplied the numbers and got the 5 times table, all the numbers ended in 5 and 0, 5 and 0. Even the multiplications, let's see, 2, 2, 4, 6, 8, 0, 2, 4, 6, 8, 0. There were patterns involved. In polynomials, there are patterns involved too. Let's take a look at the next visual and see what kind of patterns we can see. And what I've done here is I have 5 binomial multiplication problems. Each one is a bit different than the one above it. For example, the first one, x plus 2 times x plus 3. Both numbers are positive. Okay? Then we have x minus 4 times x minus 1. Both numbers are negative. The next problem has x plus 5 times x minus 2. And one's positive, one's negative. The positive number is larger. And the last one of that type has x plus 4 times x minus 6. I said the last one, but I really wasn't lying. I was lying, of that type, because we have a positive 4 and negative 6. The negative number is larger. And the very last problem at the bottom is x plus 4 times x minus 4, where one is positive, one is negative, and they're both the same number, 4. What I'd like you to do now is to stop the tape when I get through talking and multiply each of those 5 problems, come up with an answer, a polynomial. I'll give you a hint. It should have an x squared in it. You might want to check it using plugging in 10. And then I want you to also look at the answers and see what kind of pattern emerges in your mind, so that if you saw a problem, let's say instead of x plus 2 times x plus 3, you saw x plus 5 times x plus 9, again, both numbers were positive, you'd have some idea as to what the answer should look like. So go ahead and stop the tape right now, do that work, look for the patterns, and turn me back on again, and I'll be in your face. Okay? All right, now, hopefully you did what I asked you to do. Otherwise, it's pretty silly because you just heard me stop talking and start talking again. The whole idea, as we said in Lesson 1, was to go and do the work. What you should have gotten are the answers that we'll see in the next visual. If any of your answers were wrong, I would suggest that you mark them wrong, go back, do them again, and stop the tape first, and see if you get them right. Do you see a pattern? Well, look at the differences. In the very first one, where both of the numbers, the plus 2 and the plus 3, were positive, you'll notice that we got a positive 5 and a positive 6, x squared plus 5x plus 6. On the other hand, where both numbers were negative, we got a negative 5x and a plus 4. Now, you'll notice, if you think back when we did the FOIL method, that when we multiplied positive 2 times positive 3 in that first problem, we are going to get a positive 6. And in the second one, we multiplied negative 4 times negative 1, we are going to get a positive 4. In other words, when we're multiplying binomials, we multiply a positive times a positive number, or a negative times a negative, we're always going to get a positive. And the only way we can get that constant term at the end of the answer is by multiplying a constant times a constant, or a number times a number. If there's an x involved in either of the terms we're multiplying, there's got to be at least an x or x squared in our answer. So therefore, we can see that when x plus a number times x plus a number, or x minus some number times x minus a number, the answer is going to have a positive number at the end. Look at the middle terms in those two problems. Why is the first one positive and the second one negative? Well, again, in our FOIL method, we multiplied x times 3 and 2 times x, which gave us 3x and 2x. We combined like terms and had 5x. In the second problem, we had x times negative 1 and negative 4 times x. We combined those and got negative 5x. When you're adding two positives, you get a positive answer. Adding two negatives, you got to get a negative answer. So, the x plus 2 times the x plus 3, that type of pattern says we're going to have a positive number in the middle term. The x term will have a positive coefficient, with that number being the sum of the two numbers. That is, 2 plus 3 is 5. In the second pattern, x minus 4 times x minus 1, we have negative 4 plus negative 1, giving us negative 5x. The next two patterns are different because we have opposite signs. When you multiply two numbers with opposite signs, you must get a negative. So therefore, in the third problem, we get negative 10 because 5 times negative 2 is negative 10. In the fourth problem, we get negative 24 because a positive 4 times a negative 6 is negative 24. But notice the middle term. To get the middle term in the x plus 5 times x minus 2, we multiply x times negative 2 to get negative 2x, and positive 5 times x to get positive 5x, which means we have a negative 2x and a positive 5x, and adding two numbers, the negative 2 and the positive 5, with opposite signs, you take the sign of the larger and subtract, so we get a positive 3. Thus, the middle term in the answer is positive 3x. In the next problem, the x plus 4 times x minus 6, we add 4x and negative 6x, which gives us a negative 2x. So what you might say is the pattern in the third and fourth multiplication problems are that if you have x plus a number and x minus a number, the number at the end of your answer, the constant term, must be negative. And that if you multiply, for example, x plus 4 times x minus 6, again we saw it was negative. If the two numbers we're multiplying, if the larger one is the positive, then the middle term will be positive. Though we had the plus 5 and the negative 2, we got a positive 3x in the middle term. If the two numbers, the larger number was negative, like positive 4 and negative 6, when we added the positive 4x and the negative 6x, we got negative 2x. The last problem is interesting because the x plus 4 and x minus 4, we have 4 and negative 4, the same number, opposite signs. What happened? The plus 4 times x and the minus 4 times x canceled, and you should have wound up with x squared minus 16. Very special case if you're multiplying x plus something times x minus something, and the two numbers are the same, there'll be no middle term. There'll be no x term. You'll simply have x squared minus, if it's 3 and 3, 3 and negative 3, will be minus 9. If it's 7 and negative 7, it'll be x squared minus 49. In the time we have left, I'd like to go back and do a couple of more of these kind of problems. And again, follow along and try to figure out ahead of me what the answer should look like. For example, x plus 3 times x minus 7. Now, before we can start multiplying, and if you feel confident enough, go ahead and multiply, but I like to analyze it. What do I know? Opposite signs. Opposite signs means my number, when an answer I put over here is going to be negative. And also I know I'm going to wind up subtracting, and since the negative 7 is bigger than the positive 3, the negative is the larger of the two numbers, my middle term is going to be negative. And again, using the FOIL method, x times x is x squared. X times negative 7 is negative 7x. Positive 3 times x is positive 3x. And positive 3 times negative 7 is negative 21. Not done yet because I always need to combine like terms. Same place value, I can combine them. X squared minus 7 plus 3 is minus 4, minus 4x. So again, my thinking was correct. Because I had opposite signs, that's going to be negative. Since the negative was the larger of the two numbers, my answer in the middle, my middle term is going to have a coefficient that's negative, and it's going to be the subtraction of those two numbers. Let's try one more. X minus 7 times x minus 3. Notice some similarity in these two problems. I stop for a moment. I look. Negative times negative is going to give me a positive. They're both the same sign, so I'm going to add them. So that my middle term is going to be negative, as we obtained by adding. Let's go ahead and do it. X times x, x squared. X times negative 3, negative 3x. Negative 7 times x is negative 7x. Negative 7 times negative 3 is positive 21. Combining the like terms, I get x squared minus 10x plus 21. And again, because I multiplied two numbers with the same sign, negative times negative, I got a positive. Since they both were negative, I wound up adding negative 7, negative 3, and got the negative 10x. Again, I stress to you, if you haven't been able to do these, go back, rewind the tape when the lesson is done, and try to work these problems out. As you can see in the lesson we've done today, polynomials are nothing more than whole numbers that have place values that are powers of x rather than powers of 10. We can check any arithmetic in our polynomials by plugging in x equals 10 and evaluating the problem. The rules for adding and for multiplying polynomials are identical to those for adding and multiplying whole numbers. If you can add and multiply whole numbers, you should have no problems with polynomials. And therefore, it's simply a matter of practice and recognizing what you already know. The problems can get more difficult or more complex, but ultimately, if you're multiplying, the rules are the same. If you're adding, the rules are the same. The key thing, and I can't stress this enough, is until you gain enough confidence that you know that you are right, check your problems by plugging in x equals 10 to ensure that your answer, when you plug in x equals 10 into your answer, is the same as the answer you get arithmetically when you plug x equals 10 into the original problem. The next lesson will deal with factoring, which is an extension of what we've done today. So if you can't multiply polynomials, you don't want to start lesson 3. Go back and be sure you can multiply. If you can multiply, then we'll be ready for lesson 3 next time.